Hi there. Today we are finding the surface area of different shapes. Here's our definition for surface area. This formula is derived from looking at this cone and breaking it into partitions, an infinite number of partitions, and having that partition width go to 0 as we normally do with our area, volume, using that Riemann sum type of technique. So here's our formula for surface area. They've asked us to find the surface area of this cone as it's revolved about the x-axis. So let's just plop down our surface area formula, and so we're going to say surface area equals integral of from, and I'm going to be integrating this with respect to x, so our interval is, those limits of integration are already sitting there pretty for us, from 1 to 3, 2 pi, my f of x, so that is 2 times the square root of x, here's my f of x, and then multiplied by 1 plus that derivative. Well, I'm going to need the derivative, so f prime of x is going to equal 2 times 1/2 x to the, subtract 1 minus 1/2, and simplifying this a little bit, I'm just going to get 1 over square root of x. So I'll place that here. This will be 1 over the square root of x, quantity squared. Well, that makes that nice, doesn't it? Dx. Nice. Okay, so let's see what we have here. Multiplying here, I guess I'll get my 4 pi. I'm going to go ahead and bring that square root x into this square root. I'm going to combine those two. I'll end up with square root of x times the 1 is x plus, and this would be 1 over x times that x, so this would be a 1 dx. Well, that's even prettier than I thought. Then I'll just do a straightaway integration on this, and that's going to be x plus 1 to the 3/2. I got to remember to multiply by 2/3, and because of that power drop rule, and then I've got my 4 pi still sitting out here. I'm going to integrate this with my limits of integration. Whoops, you're supposed to be a 3, little bud. Put a 3 there, 1, and then I'm just going to do my number crunching. Alright, after plugging in my numbers, I end up with this exact value of 16 pi over 3 times 4 minus the square root of 2. And you could come up with a numerical approximation to this if that was asked for. For our next problem, the hardest part is just figuring out what in the world they're talking about and what do they mean. So we have this spherical cap, and we'd like to know the surface area of that spherical cap at any height that we want to choose along this sphere. So that would mean that our height is going to be dependent on that radius of A. That would be our limits of integration, and so for our surface area, we're going to say that that limit of integration is going to go from A minus h to, could be that total radius there. Our function is just the area of that arc, that sphere, and then it's rotated, so we can just use our regular circle formula. I will need to know what f prime is in order to plug that into my surface area formula, so let's just get it started. 2 pi, and then it's going to be square root of a squared minus x squared. Then I'm going to have to say multiplied by 1 plus, then I'm going to have to find that f prime of x. So taking this derivative with respect to x, that's going to be a 1/2 out front, the a squared minus x squared, then the 1/2 minus the 1 will be -1/2, and then multiplied by the derivative of the inside, which is then a -2x. Making this a little bit prettier, not much prettier. It's just going to be a -x over the square root of a squared minus x squared. Plugging that in to my formula, I have -x over square root of a squared minus x squared, quantity squared, with respect to x. So let's simplify this a little bit because it is quite messy. A minus h, I'm going to write that down for you. Just getting rid of that square there. Now what I'm going to do is get a common denominator and get this all in one chunk, and then I'm going to bring this a squared minus x squared onto the inside of that square root, multiply that. Alright, just working my little algebra there. I'm getting ready to bring this inside of this square root because they're both underneath the square root. Look at how these guys are going to cancel, leaving me with just the square root of a squared, which is just a plain old a. So I'm going to get equals 2 pi, and then I'm going to get a minus h, and just a plain old a dx here. That's nicely integratable. That would be 2 pi a x. Use my limits of integration, and then just plugging in those limits and getting my final answer. And there we have it. When I plug in the a minus h, I believe I get what it was they were after. And the hardest part is this setup here, figuring out your limits of integration, and I guess the hard part about, it's a circle that's just been rotated, so that part wasn't hard, but this set of limits of integration is a bit tricky. And then after that, it's just working through the integral in the algebra. And this straight up surface area problem. They tell me what my function is that I'm supposed to rotate, and rotate it about this x-axis. I'll integrate with respect to x. It's just throwing all of this stuff in. Here's my interval. So my limits of integration would be 1 to 2 pi. My function that they give me, which is x cubed plus 1 over 12x. Doesn't look very pretty. And then 1 plus, and then I have to take that derivative. So I think I can do that on the fly right here. That would end up being that f prime would be that 3x squared minus 1 over 12x squared. Tricky part here is I've got to square that stupid thing. Alright, that's going to take me a minute and it might be a little messy, so I'll put you on pause and you can see it. Alright, multiplying this out, combining like terms, I found that this was a perfect square. That's pretty convenient because now I can get rid of that square root, and it will look something like 1x cubed plus 1 over 12x, and I'm going to have this term sitting here just plain. Not really that that's much prettier because now I'm going to multiply all of this out, but then I'll be able to integrate each individual term, and that'll play out nicely, so I'll do that. Alright, punching this really messy thing, I get this 6145 pi over 192, and then if I want the volume of paint, I'm just going to multiply that by the 0.05 centimeter thickness. So I'll do that. And this is what I get for the volume. On to the last one. On this particular problem, we are going to be integrating this with respect to y, and we're revolving it about the y-axis. So we're going to be getting that surface area as this function here is revolved about the y. That means I'm going to have to change this function here in terms of y instead of x. So I'll do that algebra, and then we'll do the setup. Alright, now that was kind of messy, but I just used this logarithmic technique to get the x isolated, so good to get the function in terms of y. And now we're going to do the setup for the surface area. Alright, let's set it up. We're integrating with respect to y, so I look up and down this axis for my limits of integration. That goes from 0 to the natural log of 2. And then I've got my 2 pi, my g of y, which is the function that I just found, e to the minus y, then multiplied by 1 plus, and I got to take the derivative of this guy right here. It's not too bad, e to the y, and then minus 1/4 e to minus y. It's going to be that quantity squared dy. I'm going to multiply all of this out and combine it with this one and see what happens. Conveniently enough, this one worked out a lot like the other problem. When I multiplied it out and combined these like terms, it ended up in a perfect square, so there it sits. That means I'm going to be able to negate this square root and square quantity, and then I'll just multiply this out, and then it'll just be, I'll be able to integrate it term by term, and that'll be nice. Wow, and after plugging all of that in, this is what I end up with for the exact answer for the surface area. Stunning. Alright, and if you have any questions, come see me